The last CNN we're going to see is DenseNet, designed in 2017. As its name indicates, DenseNet is composed of dense blocks. Here is a research paper and a scheme of DenseNet with 3 dense blocks. Between 2 adjacent blocks, you can find what is called a transition layer. The role of these layers is to modify the feature map sizes, whereas they do not change inside the dense blocks. To do so, as usual, convolution and pooling are used inside transition layers. Here is displayed a dense block. Inside each dense block, all outputs of all layers are used as inputs for all the following layers. In this example, a 5-layer dense block is depicted with a growth rate k equal to 4. This corresponds to the number of feature maps created in each layer. Each layer takes as input all previous feature maps of the dense block, and all resulting feature maps are concatenated into one big volume, which is then passed to the transition layer. Therefore, inside the dense block, a layer operates as described by the second formula, where xl is the output of the nth layer, and x0 until xl are the outputs of layer 0 until L respectively. The function fl itself is composed of 3 consecutive operations: a batch normalization, a ReLU activation function, and a 3x3 convolution, where zero padding is used such that feature map sizes are kept fixed. Between dense block, you can find transition layers that change the size of the feature maps via batch normalization, 1x1 convolution, and 2x2 average pooling. As already mentioned, the growth rate is nothing but the number of feature maps created by each layer inside a dense block. Bottleneck layers, called DenseNet B, can be used to improve the computational efficiency of DenseNet. Bottleneck layers use 1x1 convolutions in the following way: batch normalization, followed by ReLU and 1x1 convolutions, which are followed by batch normalization, ReLU, and 3x3 convolutions. Using 1x1 convolutions helps decreasing the depth of the output volume, therefore reducing the number of parameters needed in the 3x3 convolution step. By default, 1x1 convolutions are set to produce 4k feature maps, where k is a growth rate. Finally, compression layers, called DenseNet C, are used to throw away a fraction of feature maps at transition layers. Here are displayed several architectures of DenseNet, from the most simple on the left to the most complex on the right. You can see the succession of dense block and transition layers together with a global pooling at the end of the network. The optimization procedure is almost exactly the same as before. Results of DenseNet are displayed here at the bottom of the table. In particular, results of DenseNet are quite impressive on the Cypher dataset compared to state-of-the-art methods. Note that some versions of DenseNet contain much more parameters than ResNet. You have to keep that in mind from a computational point of view when training and testing different neural network architectures.